The application simulates the spatiotemporal propagation of high-frequency electromagnetic waves, TE and TM modes, bounded within a hollow metallic pipe with an elliptical cross-section. In the transverse XY plane, the simulation maps how varying the waveguide's eccentricity transforms the spatial distribution of the fields, utilizing a finite difference gradient engine to trace continuous flux loops. These loops either terminate perpendicularly to the boundary, satisfying the Newman condition for TE modes, or run perfectly tangent to it while the field amplitude falls to zero at the conductor wall, satisfying the Dirichlet condition for TM modes. Concurrently, the longitudinal YZ plane captures the dynamic forward-traveling wave envelope propagating along the length of the guide by rendering a continuous phase shift. By offset sampling this longitudinal slice away from the vertical axis symmetry line, the visualizer preserves and displays the undulating wave patterns and alternating polarity lobes of both symmetric and asymmetric modes in real time. This dual-plane visualization effectively demonstrates how structural eccentricity scales focal configurations and couples wave mechanics within bounded environments.